another practice problem that I wanted to try to do as a part of a final exam prep. So this is problem 744 from Norton. They give us a 4-bar, and I want to try to find the acceleration at this point right here. And just from eyeballing it right there, let's call that, we want to find the acceleration of that point at theta 2 is equal to 30 degrees. So some of the first things that we want to do is try to figure out what the actual range of this thing is going to be, or do an approximation. So what I want to try to do is use the tools we have available, and just as a demonstration of your mastery of the material. So we go to useful links and resources and mechanisms links, and I'm going to use motion gen. Now I will put in an image of this thing. So we're using the pro version of this. I think this is going to be figure 714, so I will have provided that. I put this under solved problems. I haven't solved it yet. It was 714. There it is right there. So it's nice to have this utility. I wish we had the other one, but this will have to do. So let's make a linkage right from here to there, from here to here, and then link these two together. And now we're going to grab that linkage right here and make it into a triad. There you go. So that right there is apparently the limits right there. Okay, so we're going to call that one the crank, and so it can go all the way down to right about there. Okay, so let's call this the starting spot, because this is supposed to be going counterclockwise, I imagine. They didn't tell us the direction, so we're going to assume it's counterclockwise. So right here is like the lower limit of the thing, and it looks to me like it could be negative 45 degrees. That might get close. You notice that it gets close to a sticking point right there, right? So I don't want to do 45. So let's say that it's negative 30. Let's say that we're going from negative 30. We're going to want to find out when it gets to 30, and it looks to me like can it make 45? That's the question right there. So let's make the thing in SolidWorks too before we go any further. But I actually have my 45, and I'm going to look here, and it doesn't. Actually, it can make it past 45, at least according to me looking on the screen. So I'm going to make a judgment call. So what we want to do for the exam, though, is let's take a screen grab out of this just to show that's what we got right there. Boom. And let's put it into Word. And let's, so this is going to be what we turn in. Also a scan of our hand drawing stuff. So this is Spring 21, ME401, Final Exam, Example 2. And I'm going to put this in here, and let me just write that it was motion gen. Motion gen, is that one word? I don't know, motion gen. So there's the motion gen model. Okay, well, let's go ahead and make this in SolidWorks. We could do this in any order. We could have done the analysis of the thing. But maybe I'm going to write down on my sheet here some things. We could say range, the O2 range, is going to be somewhere between, negative 30 degrees to positive 45 degrees, we think. We think we can make it all the way. We'll confirm it with the SolidWorks. So we're going to create a part. And let's see, so we got a new part. And I'm going to make a sketch. And I don't know what the units of this thing are. Very, very small. I guess I could, on the other video I made them in meters, and it burned me. I made a mistake in thinking, I'm just going to keep it as inches, even though this is like ridiculously small. So this is going to be the ground link, 1.82. And let's see, so what is a sensible thickness for it? 0.2? No, that's too wide. Because there's going to be smaller links. Let's see. So I'm going to say that it's 0.1. Yeah, that sounds like it. Okay. So this diameter of this is probably at a 0.05, right? Something. 0.05. Yeah, let's make diameter of those. 0.05. And get my ugly mug out of the way. Oh yeah, just be done with this. Okay. So we're going to extrude that. And 0.05 seems like a nice thickness for that. Okay. And I'm going to save this as Norton problem 744. This is I'm going to start. This will start out with the ground, right? And now let me save it again. But I'm going to save as, and I'm going to be careful here. I'm going to save as a copy and open. Always forget that. And I'll start with the crank. So I'm going to save it as a crank. If it asks you, do you want to keep the other thing open, I would say yes, keep it open. You might even want to click on that little button so that it won't ask you that every time. So we'll change this and change that distance to 0.72. Boom. And we'll save. And then save as. Make sure we click on save as and open. And let's do the rocker next. And the rocker is 0.85. And then we go to the next one is going to be the coupler. Make sure we have save as and open. Yes. Okay. And now we're going to change this to 0.68. Right. But now we want to put in that extra point. So instead of trying to modify that first thing, I'm going to just go ahead and first off, I'm going to put a center line there. So I'm drawing a sketch on top of the thing. Put another one in. All right. So let's see. The length, that's called AP, and that's 0.97 on here. And the angle of this thing is 54. Okay, and now the other parts of the thing just need to go to a point right there, so it's easy. So I'm going to grab that point up to there, over to here, over to there. Forms a nice little triangle, and then I will just extrude that. Oh, I need to grab a hold of the sketch. Extrude that. I want to instead go up to this surface, and I'll go up to that surface. There you go. Boom. All right. And something I didn't do is turn off all of these into white. I'm going to take the extra time because it just makes me feel good to make things color-coded. I like yellow as my coupler and save. And I like green for the ground. It's dumb, I know. I don't care. And I just like the way that looks there, okay? And then the crank, almost always make the crank red because it's the active one, right? It's the action color of action. And I have loud neighbors. Loud neighbors. And then the rocker. I made them magenta in the other video. I kind of digging magenta here, so let's make that magenta again. Magenta was Blue's friend on Blue's Clues. Do you remember that? You guys watch Blue's Clues as little kids? Yeah, I remember. So let's see, make an assembly. And, you know, as we're going through here and flying by, I'm going to pin that in place and put my ground in. And then put a crank in, somewhere in there. Coupler. Boom. Rocker. Boom. Alright. And we left everything as inches, so that was good news. This thing is already fixed, so that's good news for us. We'll take that. We'll take that as a given. I'm gonna make that mate all these things up. Hopefully that you guys have had a lot of practice now. I think that's one thing that I don't have any regrets about in the class. I think it's really good that we're having a class where you get to exercise your SolidWorks skills, because it's definitely a useful thing to be a master of, right? So let's go on the back of that onto the front of this. Boom, and let's have here and here. Boom, and right here and here. So it's like a speed SolidWorks. I'm very fast. Look at that. All right, so you can see where this thing can move, right? It could go all the way down there, come all the way up to right there. So we can actually see right here. We can let's I'm gonna get rid of this mate here, but I want to see what that mate is. Let's see what that angle is. Right, that says this log position is 55, so it's good that we only went up to 45. Right, so that'll be good for us. And we can also like undo that right there. Okay, so that has gone away. So let's have a starting position. Well, first off, let's see what that starting position is. Let's go to that angle with respect to this angle. Let's make the angle. And that was also 55 degrees. Wow. So we could actually have gone from 45 to 45. So maybe we want to do that. Let's start out with 45 then. So we're going to start with 45. It's nice to have the symmetry, right? So we're going to start with 45 as part of here. So let's save this thing. We got to get out of our mates first. And we're going to save this as problem 44. So you can see that I've done the other three problems. And let me pause just for a second. I want to see what my email was. I need some coffee too. So I'm 13 minutes into this. Okay, some bright shiny squirrel must have run by, captured my attention. There you go. I'm back on track. All right, so we're going to do a SolidWorks motion thing. We'll disable that. What happened to my pull down? Oh, there it is, over there. I got to open this up. Boom. All right, so here you go is the motion analysis. Did I just turn this off? I did turn it off. It's weird. Where's the placement of that? Was strange. Anyway, let's see. We'll turn off that, suppress that mate right there. And we have to think about our condition here, right? So we're going to go now from negative 45 to 45 because that's a nice symmetrical thing. So obviously that's 90 degrees total, and we're going to go. We know that we're going to go 80 RPM, right? So omega 2 is 80 RPM, which is how many degrees per second? 80 times 360 divided by 60. That's 480. We just did this in the other problem. So that's degrees per second. And so we're going to go for 90 degrees divided by 480 degrees per second, right? It's not going to come out very well, is it? It's very, very short. 0.1875 is our time range. And we'd like to have quite a few points in between that we would like for this. So let's see for this range right in here. Let's zoom in. So there's 0.5 right there. There's 0.4. And we went 1.1875, right? So let's keep going, zooming in. And 0.1, there's, no, wait, I'm sorry. I'm getting distracted by things. 0.05, 0.1, 0.1.5. So like right here is, so let's see, 1.5, 1.6, 1.7, 1.8, 1.9. Okay, so 1.6, 1.7, 1.8. This is 1.85. Can we zoom in anymore? Yeah, there's 1.8. Okay, so here's 1.85. Here's 1.875, right to there. That's where we want to bring our thing. There you go. So I'll bring our thing up. I'm going to move him over to the side over here a little bit more. Oh, right there. So I'm going to get to right there. Okay, so that's, I think I got my goal. And I'm going to move this and make him go 80. Right, and so I'm going to have quite a few frames per second, right? Because we only have 0.1875 seconds, and I would like to have, so if we only had 480, that means we'd only have 90. But let's check that out and see if that actually is true. All right, so I think it will work right here. All right, so that seems to be going here. Let's set this to all right, so let me zoom out a little bit onto there so I can see. Okay. The real question is, did we capture the 30-degree thing? Could we make it? I would like to have at least the 1 degree per movement, and I would like to have it so that we had exactly 30 degrees. So let me do some of the post-processing thing here. Let's see what our trace path is. That's a good thing to put on there. Whoop. Trace path at that point right there. So that's where it starts. Boom, right? So let me see here. Slide that thing back right there. So we're moving from here to up there. Okay. And let's, good idea to get that angle in place. So let's go angular displacement, magnitude, and we'll have that versus that. Yeah, and we're going from 45. It looks like we went up to 49. Interesting, huh? Went further than I expected with the 1.75. Wonder why. Okay. But we got close. Close to no cigar though here. What? Oh yeah, so because that went to 1.95. Can we move this thing back to? Let's see. Let's go zoom in again. Let's see. Right here is 1.875. So let me see if it'll. 45 to 45. All right. There's really no reason to do that, but just to kind of make the thing even. All right. So let me add in the things I want to know. Things I want to know. This is just to double check the angular velocity of this piece right here, and add them on top of that plot too. Do I need to do that? Angular velocity of this face versus the flat face there. Oh, I got to do it about a component. That's what I got to do about Z. So I think I don't only need that thing. And I want to add it to that other plot. Yeah. That's what it was. Not an exciting curve there, is it? Let's take a look at angular acceleration, because that's also a good thing to confirm. And angular acceleration and z, and add it to that same plot again. No, still not all that exciting. And let's find, no, not you. I want you. I want the acceleration at linear acceleration in the x direction. We have to remember about the issue with adding something onto here that we end up that the units don't work out. So we want to avoid that messed up thing by touching it once, right? And so you have linear acceleration, have the y component, this right here, add to existing, good plot 2, boom. And the only way that I know to solve this thing, right? So let's take a look at each, see the effect, just to double conject. This linear acceleration 2, we go back and tick him again. And all I'm doing is just re-clicking on that same thing. Yeah, see, it changed. I think it changed. Looks to me like the scale changed. My limited amount of... Nah, it looks like actually this stayed the same. Let me check out my angular velocity to see if that one changed. That already looks like it's probably okay. Maybe it's been solved. Yeah, I think so. Angular acceleration. I'm just not certain. Just want to double check. Okay. Well, let's put the thing where we think it will be, right? So that's it's kind of in the position, right, where it gets up to 30 degrees, which is somewhere like right in there, right? So that's kind of close to what we're thinking it will eventually be. So let's do our screen grab of this, and it's just a documentation that we did the work, right? It's not really are we going to get much out of that, but we'll put that right there, and we'll write what this is: SolidWorks motion analysis. Boom. And these don't need to be big, right? And let's get the results. So let's pull export. And let's check them out. All right, so this guy right here is our angle. And we have 92. Let's see what incremental things they went. It doesn't look like they went. That there were fractions here. We could mess around with the number of steps and maybe get those so that they're even amounts. That would be kind of a good thing to do. But we want 30 degrees. And do we have 30 degrees? Something like that right there. All right. So somewhere in there. For the exam, we don't need to be perfect, but we might want to monkey around with it, and I don't know. It's all about counting the first step or not counting the first step. So I'm going to hide some of these just so I can get this right here and copy and paste it into here, and I'm going to paste it as a picture, very small. I don't know if anybody can actually read that. But let's see. So what we expect to get out in the x direction, I might even turn these into numbers too instead of the scientific. I don't like the scientific except for when I'm using my calculator. So somewhere like, okay, around 17.5 or thereabouts, and 115, 112, something like in there. That's what we kind of expect to get. And maybe I will do this instead here so I can read it a little easier when I get onto there. If we wanted to, maybe we could even make it just a little bit bigger by like making it float right there, because so I make the thing float. Then I need some return marks there, so just so I could see it a little bit better. We're going to make a PDF of this when we're done. So what does our time look like? We're at 25-minute mark. Now we're going to begin our MATLAB work. And we're going to try to use MATLAB to do the analysis of this piece. So I'm going to use the tools I have available under my useful links and resources, and under here, under MATLAB resources, and under MATLAB codes that may or may not work. That's not very positive thought. We have all these MATLAB codes that I have written. Most of them I did this semester, by the way. One of the things I really wanted to do was to move towards a MATLAB intensive course, and I hope to do that more in the future. So I'm going to start off with a Norton example 4.1 right here. So I'm downloading that. The Norton example 4.1 is just to confirm my my angles, right? So I'm going to get the angles. We could actually get that from Norton 7.2 as well. So the Norton 7.2 is a 4-bar where we take and find our a 4-bar where we get the acceleration, right? So that actually I could use, yeah, I think I'll go ahead and do Norton 4.2 first here, or 4.1, excuse me. Now I'm going to open this up, but of course I've downloaded it before, so it's including that parentheses 3. I need to get rid of that in order for the thing to actually run. So I'm going to put in my values, and let me go to side-by-side mode so that we could do this a little bit more easily. Okay, so D here is 1.82, A is 0.72, B is 0.68, C 0.85, and the theta that I decided to go with is 30. All right, and so everything else looks okay. So I'm going to go here, and what I decide is that we have the open and the cross, and the open looks like it's pretty good. That's 23. So I would agree. Okay, so that looks pretty good right there. So I'm going to go theta 3 open. Theta 3 is 23.29, and theta 4 is equal to 132.28 degrees right there, right? 132, I guess I could agree with that. Sure, that seems right. It's definitely not the negative 56 and the negative 165. So that was basically just a double check that I have the crossed and the uncrossed thing, just to make sure I didn't have that wrong. Let me double check here with, before we go to that. We also want to check our starting position. That would be a good thing to do. So let's check out what negative 45 is going to be. Negative 45. Well, I didn't mean to hit enter. I meant to hit run. All right, so what we're going to say is that's going to be 47.32. Okay, so let me write that down. Start theta 2 is equal to negative 45 degrees. Theta 3, we can estimate that to be as 47.32 degrees, and theta 4 it appears to be 180.62 degrees. Okay, so that'll be good for us to use in the full rotation one. Now let's open up 7.2 that we downloaded, and in doing this, let's keep track of this by way of saying, okay, so using Norton example for 2.m. All right, so what we're going to do is we're going to change the thing, just include the stuff that we changed, just copy and paste it, boom, and then output, maybe I'll even write changed. I meant that to be, okay, so we have output, the output of that. I meant this to be 30. It was 30 when I did that, so let me put this in here. Let me put this in 30. And the output of the thing was this. Okay. You're at MATLAB. Okay. And so the next thing I want to do is I'm going to use 7.2 here. And so maybe I want to mention that in here. 7.2. Maybe was that 4.2 or was it 4? I think it was 4.1 actually. 4.1. Okay. And we're going to change things. Let's see. So A is no longer equal to 40. A is going to be equal to 0.72. And theta 2 for this is going to be in the 30. And omega of the thing is going to be 80 times 2 times pi divided by 60 to get into radians per second, and alpha 2 is 0. Okay. B is going to be 0.68. C is 0.85. D is 1.82. Theta 0. Theta 1 is 0. Now, right here, we have this estimated. Let's go ahead and use for the estimated, let's use what the pose is right here. So we're going to say that it's 24, or use something close, 132, right? And hopefully it's going to come out with there. Okay, so you see I hit the run, and my output of this there. So let me, before I go any further, let me highlight the things I changed. There we go. I changed all those things. So here we go. And unfortunately, I don't have like a good output thing already set up in here. It would have been nice to have done that. I could borrow it from over here, and maybe maybe it would be nice to have this right in there, and what I'll write about the thing. And of course, now this is taking up time, right? That is going to count towards my measuring of things. But I want to have, let's see, things that I want out of this. I want omega 3. Now let me okay, let me see. I have a lot of things. Radians per second, and so I go. Where's omega 3? Just omega 3. Let me see if it works. Yep. Okay. I don't like that 2. Can I get 4? Will that give me 4 decimal places? Yeah, I like. What? Don't be stingy. All right. So we're gonna have a number of these things. So I want to have. So first off, let me go. Theta 2. go degrees, and we'll go angles 1. Oops. And not theta 2, not theta 3, theta 4 is angles 2. All right, and then we have omega 3, and I want alpha 3, which is alpha 3. And then I have ABX, all right, and so that should be radians per squared. This should be I guess inches per second squared, and I call this y. All right, will that give me the thing I want? Did I do anything wrong? Looks pretty good. All right, so here is what we expect to get out of that. Maybe I'll update. Maybe not. I don't know. Maybe I'll update the thing so that you don't have to type all this out. All right, output. Boom, right there. Okay, so these are the things that we want to do. So we want to try to measure this. So we could already actually take a look. Okay, so we don't. I did not give you what this. You have to calculate this by hand. All right, the next thing you have to calculate by hand. So we're at C, hand calculations for acceleration of point P at, okay. And now, but the next thing we want to do, all right, so we're going to calculate that by hand here in a second, but let's, well, maybe let's do that right now. All right, so we're going to calculate this by hand. I've shown this previously. It's just a basic acceleration thing, but if you know how to do this, you know how to do all the other things. So that's why I'm coming in. So if we go to chapter 7, which is where we have acceleration right here, and we take a look at this section right here, acceleration of any point on a linkage, they tell us a bunch of stuff, but the basic thing we go back to is for rigid body acceleration is a combination of translation and rotation, which is really what this is, right? So we know what the acceleration of A is, and we can find the acceleration of P with respect to A and add them together to get the acceleration of P. So from this equation, this is what we have available, so we're going to use it. We could see that in the x direction, which is real, it's going to be this plus, actually minus this. And in the y direction, this plus that, which is actually minus. All right, so let's use that and calculate it for the things that we need. All right, so we are told from our acceleration analysis here that omega, let's see, we only need to write down the stuff we need to know. So let me write down omega 3 is going to be negative 9.166. And we could, by the way, right now just take a look and see what that, compare that with SolidWorks. So we might want to do that here. We have to turn that other one, though, into radians per second, because right now it's in degrees per second and degrees per second squared. But here you go. Here's the x 43.76 inches per second squared, and y is negative 25.27 inches per second squared. Okay. Like I said here, what we could do for these two right there and there, remember those are in degrees, so let's do it off to the side and say equals there. So we want to divide by 180 and multiply by pi, pi, boom. And yes, okay, that's pretty good. You can also compare the, whoops. What is it doing there? I don't know. Boom. Let's try that one. All right, so we see that we get, it compares pretty well, right? So we had like 46, negative 46.65. So it's somewhere in between those two. And we had a negative 1.66, which is also in between those two. So looking pretty good. Got some confirmation going on. All right. So if we want to calculate this by hand, we want to get the acceleration of P is going to be equal to the acceleration of A, right? So it's going to be in the x direction. Let's start with the x direction first, dummy. All right, so x, so it's going to be x plus, and looking through here, we see, well, actually it's minus, right? So it's minus P alpha 3 times the sine of theta 3 plus del 3 right here. So minus P alpha 3 sine theta 3 plus del 3. And I don't know why that del 3 is the 54, right? So del is 54 degrees right here. Okay, and so this next one is going to be the so this is actually the tangential, right? Because it times the alpha. So now you have to have the normal, which is P times omega 3 squared times the cosine of theta 3. And this is also negative, so we have P times omega 3 squared times the cosine of theta 3 plus del. I don't know why we call it del 3, but that's okay. We'll do it. So let's shove some numbers in there. Get the yield calculator out, and we have negative 43.76 minus 0.97 is our P, because that's it, that right there. Alpha, we found, would be negative 46.65 sine of theta 3 is 23.29 plus 54, and then minus 0.97 times our 9.166 squared, so it didn't matter that it was minus, and cosine of 23.29 plus 54. Okay, so if you just go 43.76, it's minus, and 46.65, and that's minus, right? So it's going to be eventually plus 90.97 times it, and 23.29 and 54, add them, take the sign, multiply it, and so now we're going to add those together. They almost exactly kill each other off right there. So no, it's a little more positive. This one is going to be negative, so the whole thing will be negative, and we're going to have decimal place needs to be in there. We will put in. Let's start with this one, 9.166, square it, 0.97 times. Now we have the 23.29, 54 plus cosine times, and we subtract. And I get APX is equal to negative 17.55 inches per second squared. Fingers crossed. 17 points there, right in between. Yes, yes, yes. All right. Did something right. We can almost stop at this point, and because is it going to be any more? Is it going to be more? Is more going to be better? But let's do for completeness. All right, so now we want the y direction. Okay, I wrote down negative, but it's actually positive. P alpha 3 times cosine. And theta 3 plus alpha 3. And then this one, I think this one is negative. Should be negative there, and it's positive, so it is negative. So it's negative p, we'll make it 3 squared times sine. So let's put them together, all right? And so negative 25.27 plus 0.97 and negative 46.65 cosine of 23.29 plus 54 minus 0.97, 9.166 squared sine of 23.29 plus 54, barely squeezing to get in there. All right, 25.27, 46.65, 0.97, and that is going to be negative right there, right? Okay. Times, and then 23 point, lost it, was that 2929 and 54? Should probably just add those together and write that down somewhere so we don't have to type. Okay. And I think, boom, and I think I got that right, and then I'm going to subtract that away, okay, and I might have screwed something up because my brain just shifted over to the side for a second, but here 9.166 is that squared, 0.97 times, okay, 23.29 and 54, take the sign, multiply it, good, and I think I'm going to add that in there, and so we get APY is 44.27 inches per second squared. Let's compare that to our Excel. No. You son of oh, it should have been, yeah. I think I said what I did wrong. I think I did. I think the last one, I think I added it, and all of those were supposed to be negative, so that's definitely going to add to my time. I'm at 47 minutes, but let's fix it. We're simulating taking an exam. You make mistakes during exams. 25.27, 46.65 times 0.97, boom. 23.29 plus 54, I should do that in my head. That's 77.29, should have done it. Then there, okay, so I'm going to subtract that out, so that's negative 35. And now this one, come back, 9.166, 0.97 times, I don't remember what it was, 23.29, 54 plus, it was 77.29, all right, times sine times, and now subtract it, ooh, there we go, and it's still though, not really pretty, 114.7, negative 114.7. There you go. Well, okay, it's close to this one, negative 115 right there. Okay, so it compares well. I'll give it a pass. So one last thing to do that I would like you to confirm, and it's just kind of more of the same, maybe a little bit. I don't know. We're going to try to, okay, our last one, let's go for full rotation now. So there's two different versions of the full rotation now, so let's look at both of them. The 4-bar full rot. I have an alt version as well, so please check those out. We're going to open up, let's open up the full rot full rot alt. That's hard to say. And here's the full rot. I just like the full rot. Okay, so the difference between this one right here is that I've set it up and I use time as the basis for the thing, right? So we have a range of time. So that way I'm able to use acceleration. I'm able to accelerate the thing. So, but the original one just had a range of angles. Well, that's going to be useful to us, right? So that's why I didn't like just completely replace it. So this main one, where we take this range of angles and then divide it by omega, that will give us a that'll give us time, and of course we can numerically differentiate that. So that's what this is really. We're doing numerical differentiation, so that's different from doing it by hand or doing it with the equations out of Norton. That's really the fundamental difference, right? So you'll notice in example 7.2 here, we're using their equations, right? Norton's equations, but here we're doing numerical differentiation. So let's put in our numbers right here. So kaboom. Putting in our numbers for the full rot. D, 1.82. A is 0.72. B is 0.68. And C is 0.85. P is our AP 0.97, and gamma is 54 times pi divided by A. Our range is going to be negative 45, and that's going to be what, times 2 times pi, times pi divided by 180, and it's going to go all the way to positive 45 right here. So think our way through there. And how many steps are we going to have? All right, so these are the number of these are the step increments, right? So that's that many degrees. Let's see, am I doing this the right way? Yeah, I think that's, yeah, this is just by radians, 1 degree increments. So I think it's going to be close, yeah. So let me see, anything else I want to do? Oh yeah, omega needs to be in 80 times 2 times pi divided by 60. All right, and then I think for our estimates right here, what we should do is theta 3. That should be our starting thing. Remember we did this. We would take 47.32, so we know that's going to be the thing to start with in our first thing, and that's going to be times pi, right, divided by 180. Similarly, we're going to replace this guy right here with 180.6, right? So I think we're going to get, I think we have everything else. So let me see, we want to document when we did this with MATLAB. And so using, let's see, using full 4 bar full rot.m, and what did we get out of this thing? We what did we change? We changed stuff through here. So that's the stuff that we changed, and here's what we got. All right, so We don't need the velocity one, but here is an interesting one for the acceleration. Let's grab these. All right, so we go down and grab that. Gotta wait a second before that paste thing will allow us to paste, and we don't need the full width of it. Let's grab the acceleration one too. All right, so and these are versus time. What? They have negative time. I hate that. What are you gonna do? Negative time? I hate that. All right, okay, but it's negative for reference, whatever. You can't go back in the time. Yeah, it really bothers me. Just make these kind of the same size. There you go. So there's our thing output, and I don't know. I think in the other ones I also had this other issue right here, right, where now I want to try to find what the numeric values are going to be. So let's first take. I think I did this in the other one too. I need to find out what cell has the 30 degree in there. So I'm going to write theta 2 is equal to TH2 times 180 divided by pi. And evaluate it. And so now I have a theta 2. And there's only 90 of these, right? You can see that it's pretty close to being 1 degree increments. And so I'm going to see what cell has 30 degrees in it. That would be cell 76. So let me see, cell 76. I'm going to write down so I can remember that. So we want to compare several things. So just to double check that we're getting what we think we should be getting. Let's take a look at omega 3. Let's take a look at alpha 3. And then let's take a look at the ultimate thing that we want to get, the APX right here. So omega 3 in cell 76, I had to look down and see what it was. 76, kaboom. Let's see, actually, let's see here. Let's say, let's put all these things in there, right? Boom. Theta 3 is... Let's not worry about that one. Let's say here, okay, let's see, we got, this is our 76, so let's see what we have. There you go. And alpha 3, that's 76. You can see that actually 75 is probably going to be a better one, isn't it? 75 is nearly identical. And then here, and that's because of the numerical differentiation, right? It's depending on whether you're taking a slope at the first one, the last one, or like one that's like in between. And the one in between we always find is a better run. Like, so we have 16.9, but versus a 17, right? Ooh, that's not good. What happened here? Ooh, all right. We did not get what we expected. That's not good. So we have to troubleshoot that. We expected the 43, didn't we? And we expected, well, this is alpha. Wait, no. What did we do wrong there? I think we did something wrong over on this one. Yeah, we did something wrong over here. I think it's when we wrote this out. No? We got that. I didn't notice. We're wrong somewhere. We calculated something wrong, didn't we? We should be getting the same thing. Ooh, that's ugly. That's not good. What did I do wrong? Oh no. was just blasting away, just thinking I was getting the right numbers. But these don't match, and I thought they would. Didn't we already notice this? Didn't we already pay this attention to this? This is the 17.17. It matches by hand. My hand matches that. No. This is the AX. That was the AX. All right. So what we need is this needs to be the APX. That's what's wrong. All right. Maybe. And oh, that looks like that. I messed that up in MATLAB. Let me fix that right there. That needs to be fixed. Okay. So, oh yeah, we didn't get that. This is right here, though. Yeah. That's what we did wrong. Okay. So we need, let me hit this again. It's going to give me those graphs. I don't need any of those. I'm going to come back over here. We want APX and go to 76. And that, it gets close. Okay, it gets close. It's actually 75 is much closer, right? So let me copy that and bring that over here. Boom. And then in here. So we were okay. So let me go to 76 again here. 76. Boom. And of course, look, that one's much better. That's 75 right there. And that's right. Maybe this one we should use. I don't know. But we see we got it, and this is what I want to do. All right, so let's see how much time we got left. We're right at 1 hour mark. It's a long exam. All right, it took me 1 hour. It could take you 2 hours. It depends how much preparation that you put into it. During class time, we can work through this. I don't know. Do this example, maybe. You want to compare these, right? Maybe that's too much to ask to do the comparison between things. You could make a spreadsheet out of the thing, right? And then just copy and paste the thing. It says comparison, right? And so here we go. We go hand SolidWorks spell it right, SolidWorks MATLAB, although by hand is really partially MATLAB, right? But these were with hand calculations, right? I don't know why I wrote comparison right here, but we go APX and APY, right? So by hand, we said that it was negative 17.55 and negative 114.7, right? And SolidWorks, we could just put these guys in there, right? We could just say that it's and we this is probably the closer of the two that right there, so we'll put that in there. Boom, and here, boom, and then by way of MATLAB, let's see. MATLAB said this. I don't know why I had to do that. Okay, MATLAB said that, and MATLAB said that. Way too many sig figs. Boom. All right, so let me get rid of that yellow stuff here. Boom. Let's put a little border around there. We could center everything. We could make the things a little bit better here. Little decimal places onto the thing. So we could go percentage as part of the thing, but that right there is probably enough. And boom. I'm going to save this as something. And exams and final exam, example 2. also want to make a PDF of it and upload it. So it took me an hour and 5 minutes to do this. But I was talking a lot of the time about other stuff, right? But if you're not familiar with the code, and I coded a little bit, maybe I gotta update that other one. Yeah, maybe I'll do it. Yeah. Anyway, let's take a look, and I'm saving as. I don't want to save as. I want to print as a PDF, and we'll send it to my exams and example 2, and then you upload it. And have a good summer. We're done. Excellent. I think it's a pretty good measure of whether you know what you're doing. And when you go to try to analyze, all this is analysis though, it's not design side of things. I don't know, be interesting to do the other problems instead of this, but this was a long problem, but it's a long course, it's a long topic. I think it's a pretty good measure. But I don't know if anybody will watch this video. Maybe you will. Tell me if you remember, if you made it all the way to the end here, and you actually watched this. Tell me what my favorite guitar is. My favorite guitar. Oh boy, that's hard. I gotta say it's my Les Paul. I love my Les Paul. Nice black Les Paul standard. It's probably my favorite guitar, I guess. I don't know. I have the ES335. I mean, my Van Halen. I love all my guitars. I love my kids. I love them. Yeah. Anyway, have a good one.